our solar system, we know this best. We've actually been around most of the places here. We've landed on some of the places, such as Mars. What are either the most habitable locations aside from Earth that we know about, or that could have been habitable or at some point in the earlier history of the solar system? And I really hitting Mars, habitable worlds equivalent operationally to the search for liquid water. And in fact, it does look like there is kind of a permafrost water on Mars, which occasionally, even now, does become liquid, but not for very long. You'll get some melts which run out, and then, of course, as soon as they're exposed to the atmosphere and the sunlight, the stuff evaporates and freezes immediately. But this has been going on for a long time. But we have solid evidence now that there was much more water on Mars in its early history when it had more of an atmosphere and more of a greenhouse warming effect. It's got none now. Rough map about where the permafrost would be now, mostly underground. The blue regions are regions we think probably have the most permafrost now. What I am interested in is what it was in the first billion years. All right, these are interesting rock formations. This really looks to geologists like sedimentary rock. You know what sedimentary rock deposits are? That is layers of rock where mud and gunk and dirt deposited can only be deposited in a standing body, not just a river, but a standing body, quite a large body of water, a sea, or even an ocean, a gigantic lake, and then it dried up and you have these sediments left behind. So pretty solid that there is sedimentary rock on Mars. Obviously, you wanted to look at that close up. Actually, I know one person who has signed up and is on a short list to go to Mars, and that is actually the most realistic mission that I've seen to Mars because it could actually happen because it's a one-way trip. That's really the only way practically right now is to send humans on a one-way trip. This particular astronaut candidate wants to be the first mom on Mars. But we have already landed on Mars and done serious exploration, scientific measurements with unmanned probes, incredibly successful. There's a little Opportunity rover rolling around there, and we've already learned a great deal. Of course, it would be nice to, as I said, to send humans there, but we've learned a great deal anyway. In fact, that's true of the whole solar system. You can learn, in my opinion, an enormous amount without risking, and throwing away human life. There's a nice picture of Mars that looks like a winter morning there, and you're thinking, yeah, it looks a little bit like when I woke up outside Flagstaff. No. First of all, there's nothing growing there at all. This doesn't even look like the high Atacama Desert where I spend time with telescopes. There's nothing growing there, but that is not snow. That is, of course, what? Dry ice, frozen carbon dioxide, which has deposited out of the atmosphere. And when the summer comes along, it'll sublimate and go directly back into the thin atmosphere. So here's a great landing site to put the Mars Pathfinder. We saw these, what looks like floodplains. You can see that water in the past flowing by sculpted these little islands in the channel of the water. So let's land something right there on the plain. And indeed, there are lots of rocks kind of strewn around like you would see on a floodplain. And so what kind of rocks do we find here? Well, and then Spirit actually is another rover, very, very successful, which went to, this is a little bit of artist's imagination. It looked like the base of what may have in the past been a lake with a river of water flowing out of it. So these, you would think, would be some of the best places you would want to go if you're looking for evidence of ancient water, ancient oceans, ancient sediments deposited in Mars's early history. And so, yes, there are sedimentary rocks there. They have the same water-bearing or water-produced kind of rocks, carbonates and things that you see in sedimentary rocks on the Earth. There's that layered appearance. Considered pretty good evidence, maybe not proof, but pretty good evidence that there were large bodies of water at some time in Mars's past that could do that. And the Opportunity rover took some specific chemical samples of these rocks, and it's consistent with what I just said. So how did Mars lose all of those oceans or lakes that may have been widespread when it first formed and perhaps was habitable. So why did Mars go from habitable to looks like uninhabited now? I'm not even sure that there's any fossilized life there that will, at a microscopic level, little microfossils might still be in those rocks. That's a excellent, exciting investigation, which will have to send much more sophisticated experiments and possibly humans to conduct that crucial question. So we don't know the answer to that yet. But here's what happened. A smaller planet that cools off faster and therefore has an iron, that's a conducting metal core, which has frozen completely solid, not just partially solid like the Earth. So no more magnetic currents flowing around inside Mars, no longer any magnetic field. Therefore, no protection to the solar wind and radiation, well, particularly the solar wind impinging directly on the surface of Mars, not enough of an atmosphere to give you any kind of greenhouse warming such as we enjoy here. We depend on it for our existence here. We don't have any plate tectonics so that volcanoes could put out more atmospheric gases. There's very little atmosphere left. If I wanted to say in one word why Mars couldn't stay habitable, I would say basically wasn't big enough to last as long as the Earth has. That, in a nutshell, that's what all of these different problems are. Now, I could imagine some other Mars-like bodies that could have a different history, perhaps, from Mars and might still have seas and oceans surviving on it, but not Mars in its conditions for at least the last few billion years. Of course, even if there were water molecules in the atmosphere on Mars, which would exert a greenhouse effect, they're exposed directly to ultraviolet radiation from the sun, which tends to break them apart, and the hydrogens escape. So it's a hostile place. They can't stay there. It's a hostile place for any kind of organic molecules. Boy, are we going to talk about the importance of organic molecules for life. And so all of that has been mostly scoured. The surface of the planet basically been sterilized now by UV light. By the way, any of you would be, Martian explorers that want to sign up, get ready to live in a cave or a tunnel for the rest of your life. You're not going to be traipsing around on the Martian surface too much, like Matt Damon, although that was a pretty realistic movie, but not without a tremendous amount of protection from the direct solar radiation. Viking 1 and then the Viking 2 landers specifically designed to land on the Martian soil and look for actual signatures, distinctive measurements of current biological life processes in the Martian soil. And so there were several experiments that were very thoughtfully designed to make this search. I mean, aside from just a camera, look around, see if there's any weeds growing there. I kind of thought that there might be, actually. No, can't see anything macroscopic at all. So then there's the big Viking arm that scooped out underneath the topsoil. You might dig down a little bit under a rock, maybe find some soil that was where some kind of primitive life chemistry might still be protected and might still be surviving to this day. Definitely worth a shot. We took a good shot. And first of all, it was a little bit depressing to see no organic compounds, which are essential for life, these complex molecules with carbon in them. And as I said, the UV has just sterilized the surface. Maybe still there might be some organics in some protected places. That's not clear. The interesting thing is that even though they were looking for different kinds of metabolism, they put the Martian soil in different containers, tried to feed them some broth. Well, they didn't really know what Martian, life would want to eat. They gave them amino acids and water and warmed it up a little bit, things like that. God, I hope we weren't poisoning it. I mean, we were assuming, of course, that it's LAWKI. We didn't find any LAWKI. Life as we know it is all that we really can search for in these experiments, and we didn't find it, although there were a few strange reactions that happen in the soil, probably because we didn't understand exactly the strange chemistry of the soil on Mars. And these experiments were sensitive enough. They took the Viking experiments out to Antarctica, left it in the snow, and it discovered life there. It discovered microbes, just floating around in the air on Earth. So it was very sensitive experiments, but failed on Mars. I don't think that there's any life down there now, but at least at the two places that we checked, the times that we checked, and with the experiments that we had available at the time. Because this is, of course, not just about our solar system, it's about habitable worlds, life in the universe. And so I've completely left out all the outer planets. These are the giant planets, and they're all similar. They're gas giant planets. They're completely different from the terrestrial planets like Earth and Mars and Venus. In ways that you would think would make them completely uninhabitable. The Jovian gas giant planets, here's a ensemble. Obviously, they're not touching each other like that. They're quite far away, and they're much, much bigger than the Earth. And the fact that they're bigger determines why they're so different from the Earth. And why are they so much bigger? Probably, well, we'll see why. Because they're further away from the sun, and so it was colder in the outer parts of the solar nebula when it started forming planets. And so you get these big gas giant planets. That's what you'd expect. In the inner solar nebula, it was hotter, so only the more durable, hardy elements like iron, magnesium, and so on could stick together and survive the higher temperatures. In the outer solar system, these gas giants, well, first of all, they have a lot of gravity. They collected more and more matter, which brings in more and more matter, so they were able to hold on to all of their light gases. And the temperatures were lower, so the light gases, in particular, I'm talking hydrogen and helium, did not escape into space, as they all practically all did in the inner solar system. So what you have here in Jupiter is basically very much like a piece of the sun. It has almost the same composition as the sun, for better or worse. So it's a big gas ball. Saturn, similar to some extent. Uranus and Neptune, that's all the planets there are, by the way, not leaving out anything else. If you bring up Pluto, we'll have a talk about that. That's a dwarf planet. That's not a planet like these. A completely different story. Because all of these gas giant planets were cool enough and massive enough to hold on to their light elements, they're much less dense. So quite a different composition from the rocky bodies of the inner solar system. Yes, they have rings. I don't think that that's terribly interesting, except it's kind of pretty. Jupiter has rings too. Uranus and Neptune have some rings also. They're just not very spectacular. This rings is a transient phenomenon. It comes and goes when material collects close to the gravity of the planet. I'm not going to ask you that on the exam. What I might ask you about, though, is the fact that all of these gas giant planets always come with their own assortment of moons around them. And for the same reason, a star has leftover material orbiting a disk around it. When it forms, it has the makings of new planets in this protoplanetary disk. Same reason there's going to be disks of material around these gas giants, out of which satellites can form around those gas giants. And then even if satellites haven't formed around there, they have so much gravity, they're very good at capturing other objects that happen to stray by. So Jupiter has, I don't know, like a dozen captured asteroids going around it. There's so many moons around Jupiter and Saturn, they just give them numbers and so on. But the first inner ones are quite big. Some of them are practically planet-sized, and they're of interest to me. Here's the Earth. See that one there with this. It's mostly just a core of rock and then iron inside it. And there probably are cores like that in the giant planets too. It's like the Earth. It's like the Earth plus a whole ton of extra stuff that makes up 90% of the rest of the planet, which is hydrogen and helium mostly. And a lot of Jupiter, not that you really need to know this, is in a remarkable high density, high pressure form that you cannot duplicate on the Earth. Hydrogen at these pressures actually becomes a metal. It makes a metallic lattice structure. Even though they have an enormous amount of mass, even though they do have some things in common with the sun, they never get hot enough to become a star. I really want you to know the distinction between a star and a planet. So Jupiter failed by a few hundred times in mass, well, maybe about 100 times, from being a star. If only Jupiter had found the right agent. Could have been a star. No, that wouldn't have helped. But if it had been about 100 times more massive than it is now, it would have been a star because it would have had enough gravity that would have compressed the core down enough to get it hot enough to be above the magic, what, 5 million degrees temperature, where nuclear fusion reactions could have started generating its own power. It could have shined by its own internally produced starlight. That's my definition of a star. And it's kind of yes or no. Either you're hot enough and massive enough for fusion, or you don't make it. Our solar system, it almost made it to be a binary star system. The sun is definitely a star, but Jupiter didn't quite make it. Binaries are fairly common, by the way, binary star systems throughout the Milky Way galaxy. Funny thing is that both of those planets radiate more infrared radiation away than they receive from the sun. Why? Because they actually are generating their own internal energy. But it's not fusion. It's not what you think. It's not much. It's pretty feeble. They're apparently still contracting a little bit, squeezing together a little bit. And as you know, we saw this with red giants and all that stuff. When gravitational energy causes something to contract, that gravitational potential energy gets released. And that's what these planets are doing. We're not talking about much contraction. No, Jupiter's never going to implode. No, it's like talking about an inch every 100 years. Almost you couldn't even measure that. But that's enough to actually give off a small amount of energy. The reason I mention that, and of course, even the Earth is giving off a little bit of energy that doesn't come from the sun. Why? Because of the substantial amount of trapped radioactive elements in the Earth's core, which are now decaying. They'll decay for billions of years, produces some heat. That's interesting because it just gets you thinking about the fact that you can have heat, some amount of heat, even in the absence of having a home star. Not much. I'd much rather be near a star. That's a source of tremendous amount of heat and keeps life going and sustained on the Earth. But there might be, if you're hard up and you don't have a star nearby, there might be some other possibilities that we should not be so quick to rule out as possible habitable locations. This is an interesting fact. It's quite a bit less dense than the Earth, of course, because it's got all of that low density hydrogen and helium, which the Earth and the inner terrestrial planets lost all that stuff. It escaped. Hadn't escaped Earth's, hasn't escaped Jupiter's tremendous gravitational pull. And so it's only 1.3 gram per cubic centimeter. It's only 1.3 times as dense as water. This is the average. Of course, it's much, much denser in the interior. There's no real clear surface there that you'd call land. There's no place to land. You just go into the gas in the outer atmosphere of this star, and it just gets denser and denser and denser and denser. And then it's kind of a density of a liquid form, liquid gas, and so on. And then it gets to be kind of more solid. But, well, there's just literally nothing that you could call a simple surface. And of course, as far as we know, all of the life pretty much on the Earth and all of it that originated and so on is very much stuck to a very limited band very close to the surface. And they don't really have that in the gas giant planets. Now, of course, because hydrogen and helium be the most common elements in the atmosphere of Jupiter, you get combinations of hydrogen. I already told you these, right? Carbon, very common element, so that combines with hydrogen. What's CH4? That's the molecule, the chemical formula for methane. Nitrogen is very common, so you get ammonia. Hydrogen's very common and oxygen common, so you get water vapor in the Earth's atmosphere. That's nice. Water is not necessarily that unusual throughout the cosmos. You can get carbon monoxide, carbon dioxide, things like that. These are all the kind of simple elements, not complicated at all, 2 or 3 atoms that you might expect to form out of the most numerous, and abundant elements. So there's no surprise in that. And these are quite stable also. Just to prove to you that Jupiter is a fluid, it's rotating very, very fast. It's one of the fastest rotators in the solar system. It's a big planet, much bigger than Earth, and yet it takes about 10 hours to go around once. And to prove to you that it's a fluid, it's not a solid object, the rotation period, the length of one day, is shorter at Jupiter's equator than it is near the poles. So it's not even holding together as a solid rotating object. If you look at pictures of Jupiter, you might take a look at it. It's rotating so fast, you can actually see the thing is bulging out a little bit at the equator. The equator has less than escape velocity, but it's really bulging out there, something which is very tiny for terrestrial planets like Earth. All right. This is probably common for gas giant planets. I don't think that's very important. Just thought I'd mention it there. Jupiter has a is the strongest magnetic field of anything in the solar system, short of the sun, which has a tremendous magnetic field also. But I mean, it's so hopeless, really, in an environment for life that doesn't really matter. Here's what matters. The Pioneer and Voyager missions, and they were especially targeted to have close flybys. This is our first really close look at these different worlds. Some of them are very close to Jupiter's tremendously strong gravity. Io is the closest one. They all look different, don't they? Kind of interesting. So this is to scale here, the size of them. I told you Ganymede is bigger than Mercury. Io is interesting because it is the most geologically, volcanically active object in the known universe. It's just covered with active volcanoes. It has an enormous amount of heat coming out of the center of it. I wonder why. That's the interesting part. All right, these volcanoes are blowing stuff into outer space. Basically, there's one right there. This is a volcano. They're just all over the place. These are lava flows here, molten sulfur and things like that. Why? It's because of Io's proximity to Jupiter's intense gravity. Io is not on a perfectly circular orbit, sometimes a little closer to Jupiter, sometimes a little further away from Jupiter. Jupiter's gravity exerts strong tides on the objects the same way, I'm glad I mentioned this the other week, the same way that the moon exerts tides on the Earth. The Earth exerts tides on the moon, but this is much stronger. The lunar tide, is enough to squeeze the Earth a little bit into like football shaped. Not really, just the parts of the Earth that are fairly easy to squeeze, the oceans. Just go back and look at my picture. It was an exaggerated picture that shows the oceans bulging out. That's because of the tidal force of the moon. Now, the tidal force of Jupiter's intense gravity, being that close to a giant planet, wants to really squish Io into a football. And it does squish it. And then as Io moves around, it squishes it back the other way, then it squishes like this, then it squishes. So Io, although it is fairly solid rock, as it orbits around, every 40 hours or something around Jupiter, it gets squished back and forth by tides in its rock. That's a very strong tidal force. How much squishing are we talking about? The surface of Io, because of Jupiter's tremendous strength of gravity, it's a difference of gravity on the front side and the back side, is going up and down by a few hundred feet every orbit. That's putting a lot of energy which gets dissipated in the interior. And so that's why Io should have just cooled off. It was by itself now and been a burned out solid rock. It still has a lot of molten rock and volcanoes is oozing out even today. Very interesting. So that's the explanation for it. And, okay, that's great, but there's no atmosphere there, just a bunch of volcanoes. Away from the volcanoes, it's bloody cold out there. So I wouldn't think I'd be very interested in Io, except the same effect of Jupiter's squeezing and heating because of its tidal force of gravity is also going to apply to the next moon out, except it's not going to be as dramatic. And that's the one I want you to remember. If you remember one moon that Jupiter has, remember the second one, Europa. This one is going to a lesser extent through the same thing. There's heat being put into the inside of Europa. Not as much, not enough to make it volcanic, not enough to make a ton of lava flows. Europa is also less dense. Io is pretty much the density of rock. What is that? About 3.5 times the density of water. Europa is closer to the density of water, or it's the same thing, pretty much closer to the density of ice. There's quite a lot of ice in Europa, and the entire surface you see is covered by a very smooth crust of ice. But when you look close up, you see these are ice sheets and plates, and I want to draw your attention to something. That's why it's very shiny. Ice is very shiny. There are these very distinctive cracks in the ice all over the place. And these are ice sheets kind of moving around and breaking apart. And every once in a while, some sort of orangey stuff is oozing out. What's the explanation of this? The hypothesis is that there's been enough tidal heating from Jupiter's force of gravity on Europa that underneath the external ice sheet, the entire planet is covered with liquid ice, water. Underneath what you see here, there must be a a satellite-wide ocean that Europa has that may go down fairly deep because of this Jupiter tidal gravity heating. And these are ice plates that are floating around on, and every once in a while they crack open. And it looks to a lot of people like this sort of orange goo stuff. Of course, water is going to be oozing out and pouring out there until it freezes. Some people think that the red color may be from a rich bunch of organic molecules floating around in that ocean. Now you have got my complete attention. That is absolutely fascinating. Who would have thought Jupiter, like the last place in the world you'd look for anything habitable, may support one of the best habitable zones, except it is under a few miles of ice sheet. So fairly difficult for the life down there in the ocean. That's where it developed on the Earth, is in our oceans. Maybe simple organic reactions eventually led to molecular life forming biology and biochemistry underneath the ice sheets of Europa. And we just don't know about it yet. The conclusive proof, I would like to say, that there is liquid water flowing around there came from a close flyby mission, I guess it was Voyager later on, was specifically designed to measure magnetic fields very carefully of Europa. And the magnetic field clearly shows that you have liquid water. That's a signature in what kind of magnetic field you measure. Also how it interacts with Jupiter's magnetic field. It's a fairly complicated experiment, but most people consider it to be pretty definitive. Of course, I completely consider it to be definitive because, principal investigator of that revolutionary experiment that NASA did is Margaret Kivelson, UCLA. So, I mean, you're going to question that? Of course it's correct. Same kind of deal apparently happening in a nearby satellite of Saturn as well. Looks somewhat similar. It looks like it's got an ice covering, but it may be warmed up enough inside to have oceans of water underneath the ice surface of Enceladus. It's very shiny because of all of the white ice surface there. And further evidence, if you need evidence that, yeah, there's actually quite a lot of water just underneath that ice sheet there, if somebody could go there and drill, look around for cracks, lower some probes into that subterranean ocean. Look, on this flyby, you have plumes of what looks like steam, gas, water vapor blasting out of some of these cracks. This is looking back into the sunlight there as the Cassini probe flies quite close to it. And there, by the way, are some simple organic molecules made up of CHON, carbon, hydrogen, oxygen, and nitrogen, in these plumes, detected chemically by their signatures. I mean, that is just, if that doesn't say habitable to you, well, that's more habitable than I got on Mars. All right, and that could be today, in spite of all of the restrictions and difficulties of studying it, not to mention the difficulties if you want to be life living under, a 5-mile sheet of ice. If you have a larger body, the outer solar system bodies, because they have the light elements, they have lots of hydrogen in them, are typically going to be a combination of rock and ice. Like these moons I'm showing you, a lot of them are sort of a 50-50 mix of rock and ice. Now, if they have enough gravity, they may, probably more than the ones I've shown you here, but maybe something like Pluto, for example, a dwarf planet. There are hundreds of those, by the way. Pluto was just ridiculously lucky, or maybe we're unlucky. I mean, the guy who discovered this, um, who I met one time, was a fanatic. And so he discovered the first dwarf planet. He didn't realize that if you just look harder, there's hundreds of others orbiting the outer solar system. They're basically just kind of the same origin as comets, except just bigger. If they're big enough, they might have an internal heat source. They don't even need a giant planet around. They don't need a tidal force of gravity. They might have a heat source from radioactive decay of elements that are trapped inside them. So it is a real possibility that there might be a lot of sort of dwarf planets wandering around. Some of them are so far out in the solar system, some of them are so far away from the sun that they may not even really be held on by the sun's gravity very much. And this is picking up on a theme from one of the questioners early. Some of these ice worlds could literally just escape their star and be wandering through interstellar space. And yet they could still have enough heat to warm up an ocean underground, under their ice sheets. So there might actually be just thousands and thousands of habitable worlds out there, even not necessarily depending or relying on a home star. They may have left their home star and be, billions of miles away from it, light years away. It's just a fascinating idea. It's a speculation. I mean, it's very hard to pin that down, but there is evidence for free-floating planets which are not connected to any particular star. I presume they formed from their star in the outer parts, and then they, some disturbance, some perturbation from the gravity of a passing star, they left the planetary system, and now they're just interstellar drifters. One last thing about the giant planets that I gotta mention here. So Jupiter, I mean, I was so dismissive. I didn't say anything about Jupiter at all, except that it was kind of useless, except that it had some nice moons that I thought were cool, and it warms them up. But there is one other thing, because Jupiter has such an enormous gravity, it's before. But if there ever is any debris wandering around in orbits around the solar system, I'm thinking about comets. I'm thinking about asteroids that get a bit out of the asteroid belt. Most of them stay between the orbits of Mars and Jupiter, where there just wasn't enough material to ever get together to form a planet. It's not that a planet broke up. The asteroids just never could get together to make any planet because Jupiter's gravity was sort of disturbing them, keeping them from coming together. But any stray material or debris that's zooming around our solar system now, we're talking about a pretty high orbital velocities, tens of kilometers per second. The most likely scenario is that Jupiter's gravity will get a hold of it. And it's either going to fall into Jupiter, or it's going to fall into the sun, or it's going to be ejected entirely from the solar system. Either way, it does not last very long to fall into the inner solar system where it could seriously threaten us on the Earth. Jupiter really keeps house remarkably clean, has done so, pretty much since the time of the heavy early bombardment, which cratered up the moon and so on, and certainly did the same thing to the Earth, except that we don't have records of it now because the Earth has been resurfaced. So that's the number one most important thing about Jupiter. It keeps us safe. Its gravity protects us from other projectiles. Tunguska, Siberia. There was nobody there except this one guy. And this horrific explosion happened. Looks like I'm frozen here. This terrific explosion happened pretty much right outside his hut. Incredible. We're talking about the energy release of several atomic bombs, and the shock waves and the light and the heat and so on were felt hundreds and hundreds of miles away. And certainly the area right around this guy's hut, all the trees were flattened in a very characteristic circular blast pattern. So you can see that all the energy came from one impact, probably exploding and disintegrating in the Earth's atmosphere. And the amount of energy, this is the amazing thing people don't understand. You're thinking, wow, like 10 Nagasaki bombs or something. Yes, that is one way of looking at it. That's the correct amount of energy. It's a huge amount of watts, seconds, or joules. However, it's not an enormous amount of mass. I'll just tell you the formula. The amount of kinetic energy of an object of mass m that's moving at a velocity v, you may recall, is 1/2 mv squared. And so when you have an object that could be, for example, a fragment of a comet, which seems likely in this case, the nucleus of a comet, it's just a ball of ice and dirt, a little bit of rock. They move around at speeds that you really can hardly imagine. They're kind of beyond our daily experience, much faster than rifle bullets. They're moving around, like I said, at typically 10, 20 kilometers, maybe 20, 30 miles per second. That's an enormous velocity. You take square of that. So this massive blast here that just flattened everything was almost certainly produced by something, that's a little bit more than 100 feet across, moving at a ridiculously, insanely high kind of orbital speed that things do in the solar system. So we're at, even small objects hitting the Earth can deliver an enormous amount of kinetic energy. And this thing was just nothing, like I said, 40 meters across. But I'm not talking now about some dinky little 40-meter object, devastating a region of a square mile or so. Those are the most common debris. You can call them meteors if you want, asteroids, comets. Those are, of course, the most numerous ones, but every once in a while, a much bigger one, they're rare, but a much bigger one comes along. Guess you know where I'm going with this. Let me take you back a lot further than just 1908. Let's go back 65 million years ago. Let's do a little geology walk. Here are some rocks that were deposited. It's not a great picture here. You could actually do this geology experiment all around the planet. It's been done. And so you go and you find the rock layers. And here's some rock layers that were deposited less than 65 million years ago. Here's some rock layers down here underneath, because it hasn't been distorted and turned upside down. Here's some rock layers that were deposited more than 65 million years ago. And then here's an interesting little layer called the KT boundary. That's what geologists call it, which was deposited right around 65 million years ago. We know from radioactive dating of that. Guess what? The rock deposits before 65 million years ago are filled with dinosaur fossils and fossils of many other animals and plants, which are now extinct. Right above this boundary layer, so just after 65 million years, many of them, in fact, the majority of them, are gone, disappeared, extinct. Of course, the dinosaurs are the most famous. They're kind of the poster child for this mass extinction event, but it was an entire ecosystem that went out, all the stuff that dinosaurs ate, the plants and animals that depended on this. In fact, a large amount of all life, particularly a large amount of life that was on the surface of the Earth, just went extinct. Stuff that in the oceans, simple creatures and plankton and things like that, the microfossils of those indicate that they did much better surviving. But there was a horrific mass extinction 65 million years ago all across the planet, not just in one little geological deposit or some other. And here's a clue. There is an unusually large layer, just a very, very thin layer. It was probably just laid down in a few years, which is rich in some very rare elements that you don't normally find in rocks on Earth, iridium in particular. Just a very uncommon element, except turns out to be quite abundant, quite common in comets and meteors, actually. Yeah, that's a clue then. So the hypothesis that the giant impact, something that might be 10 kilometers across, what is that, about 6 miles in diameter, a comet nucleus, could have pulverized some part of the Earth and just covered the Earth in debris, which then settled down, and actually a lot of pieces of the comet material would just settle down into this iridium-rich layer of comet dust all over the planet. What else is in this layer? Tons and tons of basically charcoal. The energy that was released in this impact was enough to basically set practically everything on fire all over the Earth. So there was so much smoke, which it took a year or two for this to settle down as rains eventually started washing the atmosphere out. But there's no question that if this happened, that at least for the first growing season, at least the first springtime after this impact happened, it was so dark that no sunlight was getting down to the ground at all. It would have been as dark as midnight. Couldn't probably see your hand. Well, dinosaurs don't have hands. Anyway, the dinosaur couldn't even see its claw in front of it. So all the food died, the plants died, all of the animals that fed on the plants died out, couldn't survive, and certainly the top of the food chain, the dinosaurs, every one of them died out. Now, some people say, yeah, well, the dinosaurs, some of those species were already kind of on the decline before. Maybe it wasn't really the greatest idea for 65 million years ago. I'm sorry, but they were still alive. They were still cranking it out there, cranking out more dinosaurs, being the king of beasts and everything. And they just completely had a horrible year when this impact happened. Anyway, so I think that that's pretty strong evidence. But you all are skeptical, just like me. You'd want some actual proof that this actually happened. And you're asking for something fairly tough because 65 million years ago, we don't really have much of the Earth's surface left. It's been, submerged by oceans, and continental drift has moved it around, and mountain ranges have formed and so on. And so it was just kind of by luck that we found the smoking gun. Here's the actual impact crater from the dinosaur killer event 65 million years ago. There it is. Okay, not too far away from here, south coast of the Gulf of Mexico. There's the current land boundary. There's Gulf of Mexico up here. Here's Yucatan Peninsula. You have to actually do some pretty deep sonar and radar explorations. Actually, this was done by oil explorers that wanted to drill and find oil. Instead, what they found is this huge blast thing that's almost 200 miles across here that looks like an old crater, an old impact crater from a comet or a big meteor. Would have to be about 10 kilometers across. It's now partly covered up by a bunch of dirt and so on. Yucatan, some of it sticks out into the Gulf of Mexico. That crater is totally consistent with having formed 65 million years ago from a big impact. So it does appear that even now in the relatively calm, relatively protected, quiescent solar system that we live in, every once in a while we have a bad day on the Earth, and it's not easy to predict that it's coming, even with all of our current technology, although we're certainly more on it than the dinosaurs were. Nobody warned them. And it is going to happen again from time to time. And so it's something that's interesting. And it has a profound impact, pardon the pun, on all life on Earth. It can change the course of evolutionary history, just as this one did, and just as apparently several other massive impacts have done at different stages earlier in our history of the Earth's evolution, which are even harder to trace because they're further back 10,000 years on the average without being able to predict it. You do get hit by one of these things. Worst case, actually, it's not going to land in Los Angeles. That's such a small target. Worst case is it hits the Pacific Ocean. That's a big target. You get these horrific tsunamis. The first tsunamis that will come in from such an impact will be 1,000 feet high. You know how many people live within a few thousand feet of like the ocean? Fortunately, the big dinosaur killer ones are extremely rare and they only happen, well, very infrequently, millions and millions of years. So that's not likely to be, unless we just have really bad luck, we're not going to worry about those. But things that are a kilometer across or half a kilometer across can still completely ruin your entire day, actually your entire year, are a real threat. I actually looked this up. People are so funny about like risks and so on. People really have no, almost no rational ability to actually analyze risk logically. It's purely emotional stuff. And so people are insanely worried about some stuff and they don't worry about other stuff that's more serious. So people are insanely worried about air travel and stuff like that, which is ridiculously safe. Now, your odds of dying, let's say humanity, averaged over thousands of years. The average human, let's suppose that air travel continues, although TSA and it's got whatever, hopefully we'll have an improved version of air travel in the future. If we just keep on going around, your odds as a human being ultimately over thousands of years of dying in a plane crash are less than your odds of being killed by a meteor impact. Did y'all know that? But hundreds of thousands or millions of people will die from those tsunamis, but it's just a one-shot deal. Your mind can't really contemplate that. I do want you to keep in mind that dinosaur killer impact apparently played a crucial role, it would seem, in our being here. Basically because dinosaurs got thrown off of the top of the food chain is essentially what happened. It gave a chance, an unexpected opportunity for many other species that were not impressive, not doing anything, small potatoes compared to the dinosaurs. This is plant species and animal species that really suddenly had a gigantic open ecosystem that they went roaring into after everything was practically dead. And it was a whole new biological world out there, a whole new ecology. And you know which particular species I'm thinking about. I'm thinking about some of the simplest mammals. It's not at all clear mammals would have gone anywhere if they hadn't had this special unanticipated break. What I really enjoy doing when we have a live class in the classroom is I like to pass around meteorites. Everybody should get to look at the collection. We have a great collection at UCLA. These are all rocks that spent billions of years from the birth of the solar system wandering around interplanetary space, and then they crashed in somebody's desert, somebody's backyard, and they came to UCLA, and you can pick them up in your hands and feel them. They're so cool. They're little samples of the early solar nebula. Most of them, just come from interplanetary space. A few of them appear to have come from the moon because they have a composition exactly like the moon. It must have been some pieces of the moon got flung out, blasted out into space. They wandered around for millions of years and they eventually fell down in Antarctica. That's a very good place on the ice fields to find meteorites because they just sit there. A few of them, this is just amazing to me. I thought, you guys are really nuts, but no. There's a number of meteorites in our collections which almost definitely came from Mars. Think about that. We got pieces of Mars already, even before sending a probe there to take it back, which will be a very big stunt, very expensive and difficult to do. We got pieces of Mars because they're basically seems to be chemically identical to the rocks that the Martian rovers have analyzed there. So that must have been some horrific explosion millions and millions of years ago on the surface of Mars, maybe an impact, and some of these things got hurled with escape velocity off of the Mars surface. They flew around for millions of years orbiting around the sun, and they ended up landing on Earth and not getting completely destroyed and getting collected by, God, those are valuable, by the way. That's an interesting business to be in. You know what's the most interesting thing to me? If you look at the most primitive meteorites, there are these little sort of white inclusions in them, little white condensations of organic material. So organic chemicals, like based on carbon, that's kind of the building blocks of life, as we'll see later. That was all around. That was a natural ingredient in the early solar system. And now I'll tell you the most amazing thing. This was not contamination. This was not a screw up in the laboratory in Pasadena where this was analyzed. My friend used to work there, so he says that they kept it very clean. In the meteorites themselves, they found primitive amino acids, the building blocks of proteins, which are the building blocks of life. So even in some detail, it turns out that the stuff that you and I and all life on Earth is made of is not that cosmically unique or special. Life apparently took over existing building blocks and then use them. So the early oceans of the Earth, as it was cooling down and all of this water vapor and steam that outgassed was condensing into basins to make the Earth's oceans, they must have been filled up with not just water, but also some of these simple primitive organic molecules. And then something happened, something remarkable, which I think I've done everything I can now with astronomy. And now we really have to look in some more detail about what happened on Earth. Comets is basically the same deal. The thing that's so fascinating about comets, I told you before, they include a lot of ice. You don't find a lot of meteorites that have ice because it's presumably been vaporized when they landed on Earth. But comets, you can see them directly. They have a great deal of ice, and when they get close to the sun, they have a great deal of water vapor and steam blasting out. And it leaves behind a trail of this stuff. The Earth must have gotten hit by a large number of comets in its early history. And the comets come from the outer solar system. That's where they hang out now, really way out in the solar system. And mostly their orbits don't cross the Earth, but once in a while they do. That is a huge ball, of, I don't know, a few miles across of ice. That's quite a delivery system for water, even if the Earth did not have very much of its own water left because it was a bit too hot this close to the sun. We got a new supply of fresh ice from the outer solar system, and there are some astronomers or scientists or whatever, credible people, not just people at Berkeley, who think that much of the Earth's water was delivered to us from the distant outer solar system by comets. Pieces of comets, by the way, well, the comets leave a trail, don't they? Right? They go around the sun on these high elliptical orbits, and so it's very unlikely that we'll run into a comet. But what we do on our Earth's orbit is every year we pass through the trails where comets have recently been. When you pass through where a comet trail recently was, it's still a lot of junk around. It's sort of dirty. They're evaporating. The comets are almost destroyed by the heat of the sun when they have a close passage. And so what happens when the Earth periodically, every year, you can predict what day it is, when the Earth passes through these comet trails, we get meteor showers, which are fun. All these meteors, which are very impressive here, are microscopic. They're like specks. The big ones, the fireballs that look really impressive, those are the size of sand grains. Now do you appreciate what the V squared, the energy of a kinetic motion, mv squared, is? A sand grain will make a fireball flash of light. It doesn't get down to the Earth's surface, fortunately. It just burns up in the atmosphere, but it makes quite a big light show, doesn't it? Something the size of a tennis ball will make a sonic explosion at that speed. You look at the moon and you think, well, I'm sure glad I wasn't there. Man, did they have a tough time. That thing is covered with craters. There's craters inside craters there. I'm telling you, the same thing happened to all bodies in the solar system. They were all bombarded by this. It's just that we've mostly lost the records of it here. You have to look at very ancient, undisturbed surfaces with no erosion, no water, no atmosphere to see what the impacts were. That's like a string of impacts that hit Ganymede there, just like a string of comets hit Jupiter. This happened in '94. I was at the Keck telescope. This is what was observed. This is one comet breaking up into pieces and pulverizing the outer atmosphere of Jupiter. You could actually see this stuff with just a telescope from our rooftop.